Hello, hey 12s, welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so it says the graph below shows the change in the potential energy of the reaction where the limestone is changed into lime. The balanced equation for this reaction is as given below here. And then we are given the graph there indicating the change in potential energy versus the reaction coordinate. Then 5.1.1 says is the forward reaction exothermic or endothermic. Then based on the way the graph is, we already know that this are our reactants, and here we have our products, right? And then we do know if the energy of the product is greater than the energy of the reactant, then this must obviously be an endothermic reaction. So for 5.1.1, we're going to say this is an endothermic reaction, right? So they're only asking that and no reason. So endothermic reaction. So if they had asked for the reason, we'd say our EP is greater than ER. Energy of the product is greater than the energy of the reactant. Then 5.1.2 says calculate the heat of reaction. We know the heat of reaction is what we know as the enthalpy change, delta H, for the forward reaction. So for 5.1.2, when I have our enthalpy change is equals to the energy of the product minus the energy of the reactant. Now, what is the energy of the product? We can see here that the energy of the product is 420, and then the energy of the reactant, it's all the way here on the origin. So that's 420 minus 0, that's 420 kilojoules, and then per mole. So where do we take this SI unit? We can see that we are given from here, right? So always mind what you are given there in your table. It always goes as your SI unit. Then 5.1.3 says write down the activation energy for the reverse reaction. Now the activation energy, we know the formula to calculate the activation energy is to always take the activated complex, and then subtract the energy of the reactant. So always that's how you approach that question there. So, okay, now what is our activated complex? We know that it is that maximum energy that we find there. So that's 480. And then what's the energy of the reactant? Note that they said the reverse reaction, right? So do not be caught by that. So it's a trap. Then they're saying the reverse reaction. If this is the reverse reaction, then this is what we understand. Our products now become the reactants, and then where we had our reactants, we now have the products, because basically if this, we say our endothermic reaction is our forward reaction, then that means the reverse reaction is exothermic, and then obviously we are expecting it to have a lower activation energy. Then if we say 480 minus the energy of the reactants now will be 420 instead of the 0 now. So now we have 480 minus 420. That is going to give us 60 kilojoules per mole, right? And then just like that, we have our activation energy for the reverse reaction, right? And then let's go to 5.2. 5.2, they're saying the following graph represents the number of particles against a specific amount of kinetic energy of the molecules. The data for sample R and S was obtained at different temperatures, which affects the rate of reaction. So at this very moment, we are given the Maxwell-Boltzmann distribution curve, and then 5.2.1 says define the term rate of reaction. So we know that we are always expecting the definition there, almost about 99.9% of the time. So rate of reaction, we say this is the change in the concentration of the reactants or products per unit time, right? That's how you are supposed to define it. Easy, 2 marks. Then what does the area to the right of line T represent? The area to the right of line T, what does it represent? So that one, we say that represents the number of particles. So we know that the area after this point here, which we know it to be the activation energy, will have to be the particles. So it represents the particles with sufficient energy to collide. With sufficient energy to collide effectively, right? So this represents the particles with sufficient energy to collide effectively, or simply the particles that have energy that is greater than the activation energy, right? So all these particles that are here, they can produce effective collisions, right? Then 5.2.3 says which sample was at a higher temperature, right? Only sample R or sample S. Now, this is based on you having to know the shapes that occur as a result of each and every factor that affects the rate of reaction. So we do know that if temperature is a factor, then we only just supposed to see our graph kind of skewing to the right here, and then still maintaining the same height. But then if you look at R, you can see that R has became wider in terms of the number of particles here. So the number of particles have increased, indicating that this was the graph. Graph R is for an increase in concentration, but graph S kinds of shift to the right, allowing for more particles to have sufficient energy to collide, right? So graph S would have to represent the effect of temperature because it is tilting more to the right. Then for 5.2.3, we are going to say sample S, right? And then 5.2.4 says explain the answer to question 5.2.4, 5.2.3 by using the collision theory, right? Then we are obviously explaining the collision theory due to temperature. So for 5.2.4, we're going to say an increase in temperature, increases the kinetic energy of the particles. So kinetic energy of the particles. And then now, since it increases the kinetic energy of the particles, we say more particles will have sufficient energy to collide. Will have sufficient energy to collide. So what is this sufficient energy to collide? This is the energy that is greater than the activation energy. So the EK of the particles will be greater than the activation energy, right? Now, if more particles have sufficient energy to collide, this obviously will resulting in more effective collisions per unit time. Resulting in more effective collisions per unit time. And then that's just how you are supposed to go about it, as easy as that. So you say an increase in temperature increases the kinetic energy of the particles. More particles will have sufficient energy to collide, meaning more particles have a kinetic energy that is greater than the activation energy. Then this will result in more effective collisions per unit time, thus increasing the rate of reaction. Thus increasing the rate of reaction. So that one always goes as our concluding statement, thus increasing the rate of reaction. Yes. Hey, Nice, nice. Let's proceed. So we are not done there. Questions still continue. So 5.3, we are given that 11 gram of magnesium ribbon reacts with a 0.25 mole dm cube hydrochloric acid solution at a temperature of 25 degrees Celsius, room temperature, that is standard temperature, according to the following balanced equation. So we are given magnesium reacting with hydrochloric acid to form magnesium chloride and hydrogen gas, which we know that that hydrogen gas is mainly what we use to measure the rate of reaction because it is a gas. Then 5.3.1 says use the graph paper that is printed on the last page. Obviously, we don't have that graph paper. Then it says plot a graph of this result. So let's just try to draw the graph here. Then like that. So the most important thing when it comes to drawing the graph is just making sure that you have a consistent interval, right? So a consistent interval is key. Then if we are to consider time, we always know that our time here is the independent variable. So this goes to the x-axis and this goes to the y-axis. Then we have our 1.0, and then we have our 1.5, and then we have our 2.0. So I'm trying to make sure that the spaces is even there, then 2.5, and then 3.0. So it might not be as even, but then just that. So when it comes to this one, we can see that there is no interval in these ones here. These are just random volumes, but then we cannot just say 0, 17, 25, 30. We need to make sure that when we are filling in our graph here in the y-axis, we maintain an interval that we're going to follow there. So it's up to us what we choose to do with that one. We can choose to have an interval of 5. We can choose to have an interval of 10. But then let's just keep to an interval of 5 because this is only ending at 35. So it is doable. Then 15, followed by 20, followed by 25, followed by 30. And then lastly, we have our 35. Now we can include 40 just for the fun of it. Then we have volume of hydrogen gas, and then it's given in centimeter cube. Then down here we have time, and then note that our time is given in minutes. Remember, we said we are not only restricted to our time being in seconds here. That's why when we define, we say per unit time. So that means we can use any unit of measurement, whether it be second, minutes, or even hours if it's possible. But then most of the time we just stick to seconds and minutes. Then obviously you want to plot your graph here. So 0 to 0, your first plot will be here. Then 0.5 to 17. So we can predict 17 to be somewhere there between 15 and 20. And then we have 1.5 to 25. So 25, it appears there. So we can just put it there. Then 1.5 to 30. 30 also appears there. So there we go. And then we have 2.0 to 33. So 33 can be somewhere between 30 and 35. So we can predict it to be there. And then we have 2.5 corresponding to 35. So we can see 35 there. And then 3.0 also being 35, which obviously if we see our volume no longer increasing, this would have to indicate that we have came to completion with the reaction, right? So all you have to do now is join all these points to form a smooth curve. Voila, just like that. And then now you have your graph drawn, right? So nice. And then all that for 2 marks, obviously they would have already given you the graph paper. So it's kind of will make things easier. All you just have to do is fill in this and then just have your plots there and combine them to make a graph. Then 5.3.2 says, use the graph and explain what happened with the reaction between 2 minutes and 3 minutes. So now between 2 minutes and 3 minutes, they're asking what happened between 2 minutes and 3 minutes. Okay, then we have 5.3.2. It says, use the graph and explain what happened with the reaction between 2 minutes and 3 minutes. Now, if you are to check between 2 minutes and 3 minutes, just here, we can see that what happened with our graph is that now the graph was starting to be smooth, or the gradient was starting to be smooth, which obviously, if we have to explain for 5.3.2, when we see the graph being smooth, it can only mean that the gradient was decreasing. So that gradient decreases there, right? Remember, smooth curve means the gradient decreases. Then if the gradient decreases, that means the reaction rate decreases. And then why is it so? It could only mean that the reactants were now used up. So reactants were used up, right? So reactants were starting to get used up there, which was slowing the rate of reaction, right? So that's how you explain that. Every time you see a smooth curve, it means that the gradient is decreasing. If the gradient is decreasing, that means the reaction rate is decreasing, and that is caused by the reactants being used up, right? And then 5.3.3 says, in a second experiment, the concentration of the hydrochloric acid changed from 0.25 mole dm cube to 1 mole per dm cube. Draw a new curve on the same graph paper to show what effect it will have. Label the new curve X. Now we can see that this is an increase in concentration, and obviously an increase in concentration we expect it to have an effect on the rate of reaction. How? We are expecting, number one, our rate of reaction to increase. How are we going to show that in terms of our graph? Obviously, if the reaction rate is increasing, that means the gradient is increasing. So we are expecting to draw a steeper graph. And then number two, we are also expecting this reaction to come to completion faster, right? So that means this reaction will not be coming to completion at 2.5, but then it will be coming to completion at a much, much faster time, or at a much lower time, right? If we can put it that way. And then that means, number one, what they want to see in your graph is you have drawn a steeper graph. You have drawn a steeper graph. And then look, it comes to completion faster, right? So it comes to, so where it starts to bend and become horizontal. So where it starts to bend and become a flat line, so it is occurring much faster than this one. So this one is becoming a flat line at 2.5, but then this one we can say it starts to become a flat line maybe at 1.5. So this here would be indicating that the rate of reaction is faster, because remember, it comes to completion faster. And then again, the fact that we have a steeper gradient here also indicate that our reaction rate is faster, right? So they say we must label this new curve X. So let's label it X. So remember, we do not have any true values, so we cannot necessarily plot any values here. But then it's just a matter of showing the shape. So number one, they are marking that you have a steeper gradient, and number two, that you are actually showing that the reaction will come to completion much faster than the original curve. Okay, so let's proceed to the final question. We have 5.3.4. It says, assume the molar gas volume at 25 degrees Celsius, room temperature, standard temperature, is 24.47 dm cube per mole. Calculate the volume of acid that was used in the first experiment when the reaction was completed, right? So they want what? The volume of acid. What acid are they talking about? Obviously, they're talking about this one, the hydrochloric acid. Now, assume that the molar gas volume is 25 degrees Celsius, and then at 25 degrees Celsius is 24.47 dm cube. Now, what are we going to do here? We want to get to our hydrochloric acid, but then we know that the one that will be produced at STP is our gas. And then we are also given information here on the gas. So it makes sense that we can start by calculating the number of moles of the gas. So for 5.3.4, to complete our step one, we will say step one, let's calculate the number of moles. Calculate number of moles. And then by doing what? By saying N is equals to V over Vm, because this gas here is produced at STP and we are already given the molar gas volume. So this is N is equals to, but our volume, which one are we going to use? We are obviously going to use the volume of the hydrogen gas when the reaction has came to completion. So when the maximum gas that is produced when the reaction has came to completion is 35 centimeter cube. Note that it is given in centimeter cube, so pay attention to that. Now, because we are performing this stoichiometric calculation, we have to make sure that we divide this by 1000, so that we put it there in terms of our decimeter cube, right? Because also our molar gas volume is given in dm cube, so we want to maintain the same SI unit there. So we have 35 divided by 1000, which will give us 0.035 divided by 24.47. Now at this point, you want to just punch this into your calculator, and then it gives you 1.43 times 10 to the exponent of -3 mole. Obviously, if you got it in a normal form, that's something like 0.00143. It's also correct. Right, so whether you wrote it that way or this way, it's one and the same thing. Right, then step number 2, you want to use the coefficient ratios, right? So you want to use the coefficient ratios. Now remember, what are we looking for? We are looking for the hydrochloric acid. So now we can say we have the number of moles of H2. So let's compare H2 to hydrochloric acid, which we're going to say this is 1:2, right? And then our number of moles for this is 1.43 times 10 to the exponent of -3. And then here we have X. Now to calculate the number of moles of hydrochloric acid, we obviously need to cross multiply that. And then we have our number of moles. As we cross multiply, we have 2.86 times 10 to the exponent of -3 moles. Right, but then what are we looking for? We are looking for the volume of the acid. So step number 3, we already know this is where we calculate for the required value. So step 3, calculate for the required value. Calculate for the required value. Then what formula can we use to calculate the volume now that we have the number of moles? We can go ahead with C is equals to N over V. And then why that one specifically? Because reading there, we are told that at 25 degrees, our hydrochloric acid has a concentration of 0.25. So what we're going to do now is that here we're going to substitute our 0.25, and then we have our number of moles as 2.86 times 10 to the exponent of -3, and then we have our volume. So to calculate our volume, we do understand we need to say 2.86 times 10 to the exponent of -3 over 0.25, right? And then punching that into your calculator, you now have your volume as, so your volume, allow me to write it here, your volume is now 3.67 dm cube, right? So let me just demarcate it here. So that's it, that's your volume. right? That's your volume. So from here, you are going here, right? From here, you are going there. And then that's essentially how you could have calculated this question there, right? So with all that being said, please watch the video as many times as possible and just try to understand the approach that I took into answering this question. And then if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.